Oh. I'm going to deliver it from there.
Okay, I think everything's good now, and we're also live streaming with a 2 minutes delay. Let me press OK. Yeah. It's from yours then.
Yes.
Okay. Yeah. Okay. Great. So welcome everyone. Thank you for joining us today. We had this small change in the room, but hopefully no one got lost. So we will do today's sessions. We're going to focus on processing in memory architectures. And Zhiheng is going to introduce his student for today.
Thanks. Hello, everyone. Sebastian Thomas is a 5th semester bachelor student in computer science. His interests including writing backend application and weather data processing pipelines. Besides, he's also interested in embedded system and the interaction between hardware and software design. In his free time, he likes to dive in the lakes around Zurich, also in winter. Thank you. Let's welcome Sebastian.
Thank you so much. Also welcome from me. Today I'm presenting OptiPIM, a framework for optimizing processing in memory acceleration using ILP. OptiPIM tries to solve the problem of mapping the data and computations that we have in some programming language and map them onto the respective PIM architecture. Existing solutions often limit indexing patterns, ignore some specific alignment that PIM requires, use heuristics, which makes them quite inaccurate at times, or use brute force, which makes them very slow at generating these layouts, or just misestimate the cost. So they would generate a perfect layout if they estimated the cost correctly, but they're just not able to estimate the cost correctly. So what OptiPIM tries to do is provide an accurate and fast and architecture agnostic, so working for multiple hardwares, a mapping for processing in memory layouts. The authors propose OptiPIM, which uses ILP, so integer linear programming, to formulate the data layout and also map the cost. It uses a data layout aware and architecture independent representation of the computations and the data, and they implement OptiPIM in MLIR. In total, we can see that OptiPIM produces mappings which are at least have a 1.8 times speed up over existing PIM mapping solutions within less than 4 minutes, and they model the costs accurately to less than 3%. First of all, let's look at what PIM and PIM mapping is all about. So processing memory tries to solve the problem that we have, which is the big data processing problem, because data movement takes a very long time in current architectures, and the compute actually can take less than 20% in current CPU designs. So we try to use closer chips, which can compute closer to the DRAM so that the memory movement doesn't take as long. And they also try to use large bandwidths so that we can use SIMD easier. For this, we have 2 solutions, processing near memory and processing using memory. And you can see 2 architectures here. One is the processing near memory architecture, which you see on the left. In this architecture, you can see that we have some specific chips that are presented near the DRAM, and there they can compute on a larger amount of bits than current CPUs can, and the data transfer time also is lower because they're quite close to the DRAM. On the other side, here on the right, you can see the processing using memory architecture. So the compute is actually done directly in the DRAM and not near the DRAM. Why is PIM layout so important? Well, here on the left side, you can see I've just put white dots above all of the places where probably no computation can take place because there is an inefficient layout. On the right side, we can see that 3 computations can take place at a time using SIMD, so single instruction, multiple data. On the left side, if we have bad, basically layout, then there can only be 1 of those computations at a time, and then we have to do that over twice again. So the better the layout is, the less time it takes, and also the more energy efficient it can be. Mapping this data onto processing in memory chips requires like aligning all the computation and data so that you don't try to do computations on data that's not there. And we map them onto processing in memory units, which we also call compute units or just PUs. They use high parallelism so that we can use SIMD and try to reduce data reshuffling. So that means that we try, once we've used some data, we've moved that close to one processing memory unit, that we then don't have to move that specific bit of data again somewhere else to some other processing memory unit, but that we just use one processing memory unit for each bit or byte that we're trying to do some things on, and do all of that in very closely. Existing mappers include heuristic-based mappers, which try to do this layout based on some heuristics, like, for example, data locality or avoiding conflicts within different banks. But those often only use like 1 or 2 heuristics and don't take into consideration everything that goes into generating a PIM layout. The other approach that is widely used are search-based, which just exhaustively tries to search all combinations. Some of them also use randomness to cut off some paths that don't look promising. And also sometimes, which also the authors of PIM do, is just cut off at some time because the computation would just take too long and take the best result you've generated from here. So what are limitations of current PIM mappers? When they use heuristics, they estimate the cost based on some few heuristics, but this is suboptimal because they don't take into consideration all the facts about processing in memory and the specific architecture they're using. Some of them also use brute force, which is slow, can take up to hundreds or thousands of compute hours to generate the mappings for one compute model. ASIC-based models is another type of model that is also used in the OptiPIM paper to compare against, but those are actually not processing in memory layout generators, but those are layout generators for other custom chips, which then obviously don't abuse the specific PIM things, but only use the things that usual integrated circuits, custom integrated circuits have. So they use some cost models and also try to solve this sometimes as an ILP problem, but they can't take into consideration all the advantages and disadvantages PIM has. So they have a quite inaccurate cost model. And the OptiPIM authors note that there's not been enough research into methods like indexing patterns, and also mathematical cost modeling for PIM hardware specifically has not been researched. And an architecture-independent mapping system, because most of the papers in this space propose another architecture, and then they give you one way to generate like your data and computation layout mapping. But it is not possible to generate the data and layout for another PIM architecture. And the OptiPIM paper tries to propose a system that works for multiple architectures. What they try to do is show that this mapping can be represented as an ILP problem, which takes into consideration the layout and model the accurate costs that the PIM actually has, and implement all of this in MLAR. For understanding OptiPIM, I suggest we first take a look at linear programming. In linear programming, we try to optimize an objective function. When it's a cost function, we try to minimize it. When it's a value function, we try to maximize it. We have given some variables, which we call x, we're given some constraints which are encoded in the form ax is equal to or smaller or equal to b. And we get as output an optimal solution vector. This is here the x, which contains all our variables and set to some specific values that maximize our cost function. The difference to other kinds of, for example, mixed integer programming is that our constraints and our objective function are strictly linear, which makes them easier to solve. And our variables, sometimes also our constraints and objectives, but this can easily be mitigated by just multiplying with the smallest value. Especially our variables only take integer values and not like all the space, because linear programming as it is not easy, but very simply solved with some existing algorithms. But for integer linear programming, there are no polynomial time algorithms that can solve it accurately. Why do you use ILP? Well, the OptiPIM authors noted that the PIM layout mapping can actually be described with some mathematical equations and inequalities, which accurately model the costs, the data layout, and all the representation of the computations very accurately. And with this mathematical model, we can then use ILP, which can give us a good solution to this mathematical problem. And then we reduce it back to our actual problem and take like all of this and map it then to the specific instruction set that we have for our PIM problem. And with that, we can generate basically the code, but for an optimal data layout and computation layout for our problem. So for the ILP formulation, this slide may be a lot, but I'll explain some examples later. What we're trying to do in ILP is just minimizing the cost, which in our case is just the execution time it takes, so the number of cycles that it takes for it to be executed. The variables are mapping indices and binary decisions. So for example, do we map some computation to processing unit A or B or C? And you can just represent this as a binary decision. And as integer variables, we have, for example, loop bounds or our data indexing. In terms of constraints, we have two kinds of constraints. One is structural validity, so that our layout actually conforms to our processing hardware. So for example, that we don't use too many processing units, that we don't have too much data for too little columns in our processing unit and so on. And the other kind of constraints that we have are based on the data placement, because we need a valid data placement so that every computation and every bit of data that we have is actually present in our processing units, but also we don't map like two computations to the same time at the same place, because that's obviously not possible in the real world either. But we need to model all of this in the mathematical model. And lastly, as an output, we get like decisions and indices. What does this mean? Well, we get our optimal PU allocation, so processing memory unit allocation. We get our data layout and our computation order. So basically everything we need to then generate the code for our specific problem. For this, the OptiPIM authors use hardware abstraction, which consists of, on the top level, two parts. The one is the processing in memory units. And every processing in memory unit that you can see here on the left has some specific data layout that is then mapped to it. Every processing memory unit has some size, so a row size and a number of rows it has. It consists of some properties like the cost it takes to do some basic operations, which may be like the majority and not in SIM-DRAM, for example, or also more complicated ones in HBM PIM when we have a dedicated processor that is near the DRAM. So just everything that we have is modeled in these PIM units. And also something like the computation throughput could also be part of the modeling of our PIM units. On the other hand, we have some model that is on top of these PIM units, and that models the time it takes to load all the data into it, which is, for example, the interconnect. And then we also need to load all the data into the processing memory units. We need to load the data out of it into main memory again. And all of this is modeled by our general hardware model. So essentially, the problem that we're trying to solve is that given some loop, so here for some variable x, we try to split up this loop into multiple smaller loops, which we can then map onto our model. And the highest level of loops that we have are the processing memory unit allocations. So which computation and layout do we map to which processing memory unit? Then the second one we have is the column allocation. So which computation do we map to which column inside one processing memory unit? And this is the place where we also exploit SIMD. And computation scheduling is then the third level, because probably not all the all the data we have can be processed at the same time, because our processing memory chips can process a lot of data, but not that much data. And then we need the temporal scheduling level, so that even though we already have mapped it to some column, we still have multiple things mapped to one column, and then we split it up into several temporal layers. What we're doing with flexible indexing, which is one of the key parts in the paper, is that we are not trying to only tile our loop such that like indices 1 to 10 go to processing memory unit 1, indices 11 to 20 go to processing memory unit 2, but we have some more flexible way to represent our loop bounds. And this means that we need some function that, given all of these three levels, we can generate all of our integers from 0 to the number of inputs that we have. And also in the other direction, that every index only appears once in our function, because we don't want a computation to appear twice. So our function needs to be bijective linear and mapped to all integers from 0 to lx minus 1. And actually, if you look at this, these are all the possible combinations that you can have. And at least one of them always has to be 1. Because if the smallest one were 2, for example, then we could never reach the index 1, because we're only like adding the linear combinations of them. So we need at least one of them to be 1. This slide is probably the most complicated, but don't worry, I won't explain all of it. I'm just going to focus on one of them, which is the original loop bound and how we are splitting up the loop bound. You can see that OptiPIM has a lot of constants and variables, and these are not even all of them. And then for every of these constants and variables, you need some constraints, not only one, to make them even valid. So let's just focus on this one. And what we have here is that the number of processing units that we use in our representation, which is numsys sub u, has to be smaller than the number of processing units that we have. And the same also has to hold for the columns and for the temporal scheduling within the columns. If you're very interested in the maths behind this, I can highly recommend the paper, because they have a few pages just detailed on explaining some of the constraints and so on. And they go very much into detail on the mathematics. But my mentor said that I should not worry about the mathematics too much for explaining it, and rather explain the concept of how it works. So let's continue with how OptiPIM is actually implemented. So now we've seen how we set up the ILP, so all of the theoretical knowledge. So now we worry about how do we solve this ILP. And there are also some nonlinear terms. So it is not a strictly linear, integer linear programming, but our solver that we use, which is Gurobi, a proprietary solver by Gurobi optimization, can actually handle those nonlinear terms. Gurobi is a company which makes a lot of money by providing the solvers for some mixed integer, interlinear programming, linear programming, and so on problems. And we use it in some stage in our pipeline, because we need, once we have lowered our PyTorch, which is our input, to the LinAlg dialect, MLR LinAlg dialect, then we do some calculations to make it, to optimize it. And then we use OptiPIM to generate the PIM mapping. And in this third stage, then we use the Gurobi to actually give us an optimal solution for our integer linear programming problem. Once we've got all of this, then we can actually allocate the memory, allocate the buffers, and generate all of the instructions that we need to execute on the processing in memory hardware to actually make our program run. So how does OptiPIM actually perform against other things? So the first thing that we can see is that the mapping generation time per operator, and this is AI model operator, is less than 4 minutes, which is compared to other things very quickly or very slow, but we'll get to that later. Furthermore, our comparison is very, very accurately. So we have less than 3% error in some simulator that is cycle accurate against the cycles that were given us from the optimizer. And this is a very, very good result. And you can see that especially for SIM-DRAM, this is very close to optimal. And for HBM PIM, we're like within 1 order of magnitude to the actual error. And most of the times, even a lot better. So for the baselines that they use to compare OptiPIM against, we have 3 different baselines. One of them is the heuristic baseline, which just uses some heuristic, and then based on this heuristic divides the input into tiles. The tile size can, for example, be the number of lanes that we have in every PIM unit. Another one uses random search. I've already talked about this before. Specifically, for example, PIMDL does this. And PIMDL is also very close to the implementation that the authors used to compare against. And this uses some kind of random search, but the authors set a cutoff at 1 hour because, like I said, it can run up to hundreds of thousands of hours. And the custom chip implementation also uses ILP to optimize it. And to map the computations onto ASIC accelerators. And then with some minor tweaks, they've also got this to map to the processing memory architecture to optimize like the loop and the data placement. But you can see the processing memory instructions are not very accurately modeled here because this is just not possible in the ASIC implementation they've used. So compared to those, actually, which is good, OptiPIM is always better. You can see that there's a very wide spread against different ones. Let's first focus just on the SIM-DRAM, because there we can see that the custom chip implementation is very, very close to OptiPIM. And that's just because, which you can see here on the right, the compute time is just such a big amount of the time that it actually takes, because in SIM-DRAM we have to bit serially compute every single one. For example, when we do an addition, we always have this carry bit. And because we have this carry bit and we don't have special operators in some processor, but we only have the RAM, we have to process this bit serially. And that's why the computations take so long. And that's also why OptiPIM cannot optimize this so much. Whereas on the HBM PIM, where we have custom processors and we have a very good operations that we can work on. Actually, the split between these 3 stages is very even compared to the others. So this means that OptiPIM is doing a good job in this regard. And you can see that the random search is very close here, and it's also close to what the authors of the HBM paper did. So yeah, that's why this was also not so bad. But you can see that against the heuristic solution for an architecture agnostic modeling problem, OptiPIM is just a lot better. So the authors of this paper formulated the PIM mapping problem as an ILP problem. They considered some hardware-specific variables. They implemented all of this in MLIR so that it is easy to use in your own projects. And the results are that they achieve a high speed up, actually at least 1.8 times speed up over existing PIM mappers, and their mapping generation time is less than 4 minutes. And with that, I would close with some strengths that I think this paper has. So on the one hand, they try to use mathematical and theoretical computer science problems which have been solved to solve a hardware problem. And I do really like this because using some results from other fields can really bring us forward, not only in that other field, which may seem very theoretical, but can also help us model, for example, our OptiPIM data layout. They have reached a way to analytically model the cost with very small errors. And then even if you don't decide to use OptiPIM, you may even decide to run this anyway, just to see what the cost would be in a very optimal one without needing to use a simulator, because simulating all of this can take even more time. And for this, you already would have to have a PIM mapping. So you can even just generate this cost without needing to simulate all of it. It's easy to integrate in your own projects. Actually, I'll come to that later, but it's quite easy to implement it in your own projects. Just if you have lowered your specific code into the MLR linear PyTorch dialect, then you can use OptiPIM to generate some code or some representation of it, which you can then lower to the actual code that you need for your hardware. And it's broadly applicable. So it's not only applicable to one operator, but you can use it on the operators that you like in your project. You can even run them concurrently. And you can generate the mappings for your specific software and your specific hardware. And it's not constrained to some hardware that the authors have designed. What are some weaknesses of this paper? Well, first of all, like SIM-DRAM and HBM PIM are good examples, because one of them is processing in memory, one of them is processing using memory. So they show us two opposites on the spectrum of PIM architectures, but there is still a lot more that are under testing or that are already developed. And it would be nice to see even more of them tested, or OptiPIM tested against them. Then the problem of integer linear programming compared to linear programming is NP hard. And this means that scalability to huge problems or huge hardwares with probably multiple different kind of processing units and so on will be harder and harder. And there's no specific algorithm that can just solve it for us that will not get into exponential complexity. And even Groby uses heuristics to generate a good value which we want to approach, and will just cut off once we've reached 0.1% accuracy to that heuristic value. The other problem with IP is that they've used a proprietary solver. So I've actually used it now too, because they have an academic license with which you can also use it. But obviously for the industry, you need this proprietary solver, which may be quite costly. And you need it for every compilation. So you only need it once if you only need to compile your code once, but who only needs to compile their code once? Then they only have an optimal solution per operator, and they ignore some things that could be optimized by using multiple operators together, or they ignore the overheads, which, for example, when you generate the mapping for one operator, then you move that operator back into main memory, then you move that operator back into the processing memory units, because you have to calculate the next operator with them. Probably you could save in this step, so they don't try to optimize this step. And while I've said the OptiPIM is quite easy to replicate, I've actually found it quite hard to replicate. I've tried it twice on my machine, which didn't work because I have an ARM 64 core and not an x86 core. So then I tried it inside a Docker container, built with a platform, AMD 64, that did not work either. Now I'm trying to build it on my server, but even that is not easy because they have a lot of more steps than only the 10 steps detailed in the paper that are required. And it even fails like to compile, which is quite sad, because I would really have liked to show it to you how it actually works, but I've not been able to replicate their setup. And you have to clone and build LLVM from source, and that is like a GitHub repository of over 7 gigabytes. And to compile it, it takes like more than half an hour. So this is, I think, a weakness of this paper. And with this, let's come to a discussion. So the first point I've thought about, now we have like a way to probably model our costs. We have some examples, applications where we've already used processing memory. So for example, matrix multiplications. And when we include pre and post processing costs, could we maybe decide whether processing memory would be worth it or not? So I think the first thing to think about is we need some way to gauge the transfer cost it takes for us to move everything into the processing memory units. And they include some of that in the OptiPIM paper, but not all of the costs that it may have. So we should definitely add that cost. And also, we could probably add like some kind of Boolean variable, which takes into consideration the transfer cost it takes, plus the cost that we have given from our OptiPIM solver, and decide against some CPU processing cost, whether it is worth it or whether the CPU processing cost is smaller than to process it in memory. But maybe some of you can think about a problem that we could have with this formulation that I've put on the board at the moment. Okay. So for this, we would need estimations for the CPU processing cost. And this is not a problem that has been solved yet. We could try to estimate it, but especially since we have like the processing memory units are pretty simple to replicate because they only do one thing. But our processors, when they execute an operating system and then some specific processes on these, the caches can be cleared between two instructions. So it is very, very hard to actually know how long it will take to run a program on a real hardware. And so I think this could be the biggest problem when trying to decide whether the processing memory is really worth it or not for a specific problem. Then let's get to a different point, which is how could we model multiple operators? So the first thing I've thought of is what kind of optimizations could we do between or after each OptiPIM operation, mapping generation for one operator. I've already touched about this before, but maybe some of you remember it. What's the problem about this that the OptiPIM paper currently has? Okay, the OptiPIM paper has the problem that it only cares about one operator and not what happens between these operators. And we would probably like to remove redundant transfers from into main memory. And maybe once we've generated one operator, it may even be worth it to take a less optimal way of that our processing memory layout has been generated, because then we don't have to reshuffle between these processing and memory units. So it may even be worth it for the second operator to have a slightly suboptimal mapping if it were only this operator, if we could include the first operator and the reshuffling cost it takes between those. But obviously, data reshuffling again needs to go to main memory. Main memory is large, and we have the problem about virtual memory. And then we have multiple layers of caches between them. So yeah, this could also be a hard problem to solve. And then a few weeks ago, we already talked about operators and multiple operators. Maybe anybody remembers something that could help us model multiple operators at once. Okay. I've thought about how about we add operator fusion. So try to fuse two operators. For this, we may have some way of given some MLR LinAlg PyTorch dialect code. Can we generate a code that is better, which combines multiple operators? But then our problem is again, is it even worth it to fuse two operators, or is the cost of doing that higher than just processing them sequentially? But again, we have OptiPIM, and OptiPIM can give us a cost function, or has a cost function which is very accurate. So the only thing that we would need is that both of these, so the fused operator and the individual operators, are given to the PIM mapping generator, and it can then decide whether the fused operator or the two single operators are better to run. And the last discussion point I would like to touch on is, does OptiPIM also maybe can be used for more things than only PyTorch? So I've mentioned the PyTorch MLR dialect. PyTorch MLR is a MLR dialect which PyTorch can be compiled into. And it is because MLR, if anybody doesn't know, it is a compiler framework that allows, in comparison to LLVM or in combination with LLVM, to use your custom dialects to have some intermediary representation of your problem. And now we have this for the PyTorch MLR dialect, but maybe this could also be used for other problems. So there are two things that we could do with that. So either we transform our problem that we have, we compile it down to the linear dialect from PyTorch. The other thing would be to adapt for OptiPIM to not only take this linear dialect, but also take our custom dialect. So yeah, there are a few examples where this could be very useful, especially those are like tasks that are very linear algebra heavy, which are very heavy in terms of the data movement and computation on a lot of data, everything that processing in memory is good with. Yeah, and then we could try to get another MLR implementation or dialect, which is easier to lower into than the PyTorch linear MLR dialect. And then we could try to optimize this one to handle specific cases, like, for example, sparse matrices. But once we get into sparse matrices, there are a lot of representations of those. But then if we know that it's a sparse matrix, then the processing cost that the sparse matrix takes in the PIM representation hardware that we have, then it may not even be worth it. So there we can get back to the first point in our discussion, which was, is it even worth it to use processing in memory? And if, for example, with sparse matrices, there's already been a lot of research done into that topic. And maybe we know how long it takes or how long we can expect it to take in most cases to generate, to handle this operation on the CPU. And then maybe we could decide whether it is worth it to handle sparse matrices on the PIM architecture or in the CPU. But for this, we would need a lot more research, and this is not directly a result of OptiPIM. So thank you very much for your attention. This was OptiPIM.
So any questions from the audience or comments? Thank you.
Thanks. Maybe I have one question for you. So you mentioned in the vagueness that the linear programming is an NP-hard problem. So how does this work? Find an optimal mapping method using this NP-hard mechanism?
Sure. So the problem is that we cannot say that it is optimal. But what, for example, the Gurobi solver, so how it works is we just add some variables to it. So I've explained with variables and constraints, we can add variables which are binary or integer or also other types. Then we add some constraints to it, which can be any kinds of constraints, but they have to be linear. And then we have to model our cost function. And our cost function we can set to, for example, maximize or minimize. And actually what the result of this with Gurobi is, first of all, it tries to pre-solve it. So it generates like all of these linear algebra matrices and vectors. It tries to get a feel of how this matrix looks, because it may be a matrix with a lot of zeros or a lot of ones. It may be a very regular, very irregular matrix. And then it tries to get so it tries to reduce the size of this problem. Then it tries to get some heuristic value for it that it is trying to get to. And then what the output of this is it always gives us a percentage. And actually this percentage gives us the distance that we are from the optimal or pseudo-optimal value that we have by having our heuristic. And then it tries to get as close as possible to this heuristic. And at the end, it says no other solution better than, and then our cost. This doesn't say that so in some cases, there is no better solution. And in some cases, this is just the local optimum they've found by using this heuristic value. But since this is an NP-hard problem, you would have to try all of them to actually generate an optimal mapping.
Do you know if it also works on mixed architectures? So if you have a processing near and processing using memory?
Two at the same time.
Yeah.
I've not been able to replicate the setup. I wanted to try it out. I think it does not, because so the things they have given, the constraints and the variables that they're using are highly dependent on the input file which is generated for each architecture. But of course, that's something that would be possible. So you would just have to add more diverse constraints. At the moment, they're adding constraints that are pretty uniformly for the architecture, because like whether you want to map it to some column or so is pretty uniform again along the whole architecture. I don't think OptiPIM is able to solve this at the moment. So for multiple architectures.
Okay. Thank you.
Yeah, so I have a question related to heterogeneous computing. So normally PIM is because near memory processing has got fabrication limitations. So it has got weak compute capacity. So you always pair it up with some accelerator like GPU or an ASIC. And how will OptiPIM work in that scenario? Because it can be that the data mapping that is required by the PIM can lead to more bank conflicts when it is required by the accelerator. So do you think OptiPIM, or have you seen OptiPIM if you ran it, whether any such data mappings came up, and how it's going to perform in short?
At the moment, as far as I've read, OptiPIM only tries to solve the problem that we have given one operator and we want to map it to some specific PIM architecture. I don't think it takes into consideration what other layout considerations there may be. So for the moving into the processing memory units and moving out of the processing memory units, so output gathering and input loading and so on, I don't think I've read anything about that in the paper. But that would obviously also be a topic that is that could also be researched, because when you have this, for example, an ASIC combined with the PIM, then first of all, you could decide, do we compute it on the ASIC or do we compute it on the PIM? And then if we're using both of them for different operators or different kinds of things in our code, then we could try to solve both of them in one ILP instead of solving them separately. And you would obviously have to add more constraints. But I think OptiPIM at the moment only supports, like, we want to map this operator to this hardware architecture.
Okay, thank you.
Okay, thank you all. I think we can then have a break until 5:15, and then we're back for the second presentation.
This one.
What? Uh, we'll check this over. No, like did you check over?
I think we should call them. We have some time. Okay, my phone is there.
Into. Just connect to the HDMI. Hey, come on now. Oh, we're stupid. We don't connect to this, and then how is it supposed to connect to that? The HDMI is now going directly to this
Okay.
and to our laptop.
If I disable this, it is indeed detecting something. If I put it in, that thing is
It's not detecting it.
okay. Right now it's not detecting it. Yes.
Okay,
And
done.
it's capturing mirror from.
Yes, that's
Happens is that Apple actually makes this to whoa. Where is the HDMI? Oh, that's the HDMI.
This is for the audio.
That's for the audio, yeah.
We have to
So let's see.
And you try calling this number because mine doesn't.
Okay, I'm not getting any.
Okay, into, yeah, that's, it works now. It detects it now. Yeah.
Okay. Okay.
Then we need audio. We need audio. Let's try audio
This is feeling like no.
Audio needs
Harsh,
to go
okay,
to
okay.
this.
Then you need to put this.
This is already on.
Yes, we can cover it.
Can you check if you hear us? Do you hear us online? You're not connected. Okay. I'm connected, but hello? Yeah, I think I can hear us. But you check also. Yeah. No, this is the other way. Let me show you.
Yeah.
You work like this.
Yeah,
Great.
can you?
Great. Okay, so then we can start with our next presentation, and Harsh is going to introduce his mentee.
So just one moment. Yeah, there you go. The next presenter for today is Sylvan. Sylvan is a bachelor student in computer science. He's in his 5th semester. He has all of his interests probably in computer science, he says that, and probably distributed everywhere else he says this. He likes computer architecture a lot. And today he'll present probably one of my favorite papers, Tesseract, a scalable processing in memory accelerator for parallel graph processing. The stage is yours.
Yeah, thanks for the introduction. So yeah, as mentioned, this is my paper presentation. So first, look at the executive summary. We have a problem with graphs, which is a large-scale graph processing is extremely memory intensive, which leads to a bottleneck due to the severe memory bandwidth limitations that traditional computer architectures suffer from. The goal of the paper is to design a system for parallel graph processing whose performance scales with the size of the input graph. The key idea is to avoid data movement as much as possible by designing a processing in-memory system to reduce the strain on external memory bandwidth. For this, the paper presents Tesseract, which is a new programmable accelerator for in-memory graph processing that utilizes PIM using the hybrid memory cube technology. Tesseract itself introduces in-order cores, which are connected to the HMC vaults. It introduces a new messaging passing system, which provides non-blocking communication and atomic memory updates without the need of software synchronization primitives. It also includes 2 very strong hardware prefetchers, which are specialized for graph processing workloads, one of them being a list prefetcher and the other a message-triggered prefetcher. And the results are quite clear. Tesseract achieves a 10 times average performance improvement and about an 87% average reduction in energy consumption compared to a conventional high-performance baseline across 5 different graph processing workloads. So this is the outline, as you can see. First, we will talk about the background a little bit. Now, in the real world, we have huge graphs. Like, for example, we have Facebooks where they have about 3 billion users, and those are all connected with each other. So this will create a huge graph. This is a simple graph function, for example. This is the PageRank computation that Google, for example, uses. And as we can see in this specific part, there is a lot of list traversal, which will become a huge problem, as we will later discover more. Now, the processing of these graphs often allows for heavy parallelizability. As you can see here, we have looping through a simple, through all the graph vertices. We can instead split this up into 2 graphs and then have 2 cores execute this. This, however, requires synchronization for atomic updates and other stuff. So with these millions to billions of vertices and even more edges, We have other problems. For example, the traversal of neighbors incurs numerous random memory accesses, as you can see in the red part there. We have the poor locality of the memory leads to constant cache thrashing, which means that the cache is usually too small, but increasing it won't help either. And a big problem with all of this is that the memory access latency that all of this incurs cannot be hidden, as the computations inside of the loops, for example, are usually very small in comparison. So conventional systems usually do not scale with larger graphs. As you can see on the right, two graphs there. We have for one 32 cores in a DDR3-based system and the other one with 128. Now that's quadruple the amount of cores. So in a perfect system for parallelizability, you would expect a 4x speed up. That is, however, not the case. Now, instead of using DDR3-based system, we could instead also use an HMC-based system. We can see there is some improvement, but it's still not exactly what we would like to see. Now using a theoretical system that uses the internal bandwidth of the hybrid memory cube, we can see on the bottom that the bandwidth usage increases by a lot, and the speed up itself is also somewhat proportional to that. Now, why that is important is because the bandwidth is usually consumed by all of the random memory accesses that we have in graph processing. And we can see that the memory locality needs a higher bandwidth for scaling. And the problem why we can't usually achieve this is the pin count limitation, which limits the external bandwidth that we can achieve. And yeah. So what we want to achieve is to optimize the system's bandwidth usage, which could lead to a better scalability. So a little background on the PIM. PIM alleviates data movement bottlenecks by instead putting the computation units closer to the memory. This capitalizes on the higher available memory bandwidth that, for example, the hybrid memory cube provides. Now, ideally, the memory bandwidth should increase with memory capacity. For example, the hybrid memory cube provides 320 gigabytes of external bandwidth and internally 512 gigabytes. And if we create a system out of this with 16 hybrid memory cubes, the external bandwidth will stay the same. The internal bandwidth, however, will increase 16-fold. So we want to emphasize on this. So the goal of Tesseract will be to design an energy-efficient system for parallel graph processing whose performance scales with the size of the graph. The key objectives of this will be to design the architecture that can fully utilize the high internal memory bandwidth that HMC can provide in preferably an energy-efficient way. We will also emphasize on the communication between all the different processes with minimal impact on performance. And there will be an expressive programming interface designed for this new PIM hardware. So coming to the design of the Tesseract itself, this is a rough overview. On the right, we have the vaults. I will come to this later on what exactly is going on in there. Then in the middle, we have the cube, which consists of 32 vaults and a crossbar network, which connects the vaults with each other and other hybrid memory cubes. And then on the left, we have the network of all of these hybrid memory cubes, which will communicate with each other in the end. So the system of all of these hybrid memory cubes will have vaults, and each and every single one of these vaults will have its own local DRAM partition. That means they can only access their own memory. Also, through the usage of hybrid memory cubes, this will allow for near memory computation, as the vaults itself can only access their own memory and compute on that. So this is the overview of what a vault looks like. It is centered around data movement. What you can see here is all of the memory space, since it's a 3D stack technology. In the red, there is the in-order core. Then we have the prefetchers, which I will come to later, and then the message passing system, which I will also explain in further detail later. So this new message passing system that Tesseract introduces will happen between any two Tesseract cores. Its main purpose is to avoid cache coherence issues among the L1 caches. Because all the memory is restricted to their own vaults, we will thereby guarantee atomic updates of shared data without the use of logs. And also a neat part that we will explain later why this happens is we can hide the memory access latency through asynchronous message communication. Now, the two prefetchers that are introduced in this paper are also extremely important, as they are tailored to the memory access patterns of graph processing workloads. For one, we have a list prefetcher for simple patterns through vertices. This will be a stride prefetcher, if you know that. And the other one is a message-triggered prefetcher that uses message information. I will also explain this later on in further detail. So the first kind of a message that will happen between the cores is a blocking remote function call. This will request, the local core will request the remote core to execute a specific function. Then the remote core will receive that function and its arguments and interrupt at the earliest opportunity that it can. Problem with this is that the local core will be blocked until that function call is resolved and it has a return value. And also every single of these blocking remote function calls will trigger a context switch in the remote core. This calls for a better kind of a remote function called a non-blocking one. This one has no return value. The local core simply invokes the function call and it continues its own execution. This, however, requires a synchronization barrier, as we would otherwise have a consistency issue, as the local core itself would never know exactly when the function call would be executed and finished. So the vault itself will have a message queue. It will store the messages it receives from other cores, but it will not interrupt as soon as it gets a single one. It will instead wait until any necessary data it has from that message will be prefetched. And then when it has enough, it will execute all of the messages in bulk, which will lead to fewer context switches. So the types of prefetching, the first one is the list prefetcher. It goes through simple access patterns like a vertex list traversal, and it employs a stride prefetcher for that. For example, you could just unroll a loop and then fetch all of the array elements in a certain size. The other more complex prefetcher is a message-triggered one. This one will be employed for traversal over edges, which will be the main cause for random memory access patterns. This one will usually be used through non-blocking remote function calls. So they will receive a message, and in that message, there will be a hint, and that hint tells the message-triggered prefetcher on what data to fetch before the message will be marked as ready and will be executed. So it will look like this. We have the message queue. Some message will arrive. Then the message hint will tell the prefetcher to prefetch the necessary data. Then as soon as it is prefetched, the message will be marked as ready. And once we have enough messages, a context switch will be triggered and all of the messages will be executed. So once again, this is the full overview. Tesseract itself uses 16 hybrid memory cubes, which are all connected in a Dragonfly system. Each and every single one of the hybrid memory cubes will have 32 vaults, and there will be 8 GB of DRAM per cube. Now, I will only briefly mention the programming interface that Tesseract introduces. The paper itself did not go too much into detail about this. If you have further questions about this, you can either read the paper yourself or ask me later. So coming to the evaluation part, the paper uses 5 common graph algorithms, which are all implemented in C++. Also 3 world graphs with 4 to 8 million vertices and 100 to 200 million edges. The memory footprint is large enough, about 3 to 5 gigabytes, but it is way larger than the total cache capacity of any of the systems that we will use, which are a DDR3 based system, 2 hybrid memory cube ones, one which has in-order cores in the vaults, another one which has out-of-order cores, and then of course the Tesseract system, 3 versions of that one that has both the prefetchers, one that only has the list prefetcher, and the other one that has the list prefetcher and the message triggered prefetcher. To note is that every single system has 128 gigabytes of main memory. So here, as you can see, very small are just the DDR3 based system and the hybrid memory cubes. We can see there's hardly any speed up between the two. So once we introduce the Tesseract system, we will see a huge speed up that is introduced. The leftmost of the 3 bars is the one that does not employ any prefetchers. The rightmost is the one that will employ both. A geometric mean is about a 7 times improvement, but there are some cases where there is more than a 20 times speed up increase. Also, the one evaluation was about the usage of the bandwidth. Once again, here we can see that Tesseract introduces a way higher available bandwidth, which will also be used for the messaging system. Yeah, so the communication utilizes the complete available bandwidth. Also, the memory latency, as already discussed, the prefetching minimizes the memory latency, and the non-blocking remote function calls can really hide the memory latency. So coming to the conclusion, Tesseract itself introduced a paradigm shift that moved the computation into DRAM. It was one of the first systems that really centered around the use of PIM. It managed to create a memory capacity proportional bandwidth, which was utilized by the messaging system to create this huge speedup it reached. We have the memory partitioning, which is there to avoid the cache coherency, and the message passing system, which itself is a new thing and allowed for the introduction of new prefetching mechanisms, with the message triggered prefetcher being a more complex version that I've so far not seen anywhere else. And in total, Tesseract achieved a huge speed up with about 10 times. It achieved a huge energy saved by about 87% and reduced memory latency by about 25 times. So the strength of the paper is, in my shift, that Tesseract really introduced the paradigm shift, which attempts to solve the data movement problem by implementing PIM using HMC. As already said, they were about the first to really introduce this and center an entire system around the use of PIM. The message passing system, I think, was an incredibly intuitive way to implement a prefetcher. List prefetcher is pretty simple, but the message triggered prefetcher is, in my opinion, something I could not have thought about myself. And as we saw in the evaluation, it definitely was cause for a huge speed up boost. The paper itself specialized only on the large graph processing, which itself is a critical computation component for modern data-driven systems. We saw that 10 years ago, we see it still today, and I think it will still be this way in the future. So Tesseract really was a milestone on helping, on creating graph processing processes. And I think the evaluation was pretty strong. They really looked at a lot of different things. For example, they did did the tests on Tesseract without the Lisp prefetchers and the message triggered prefetcher, just to show that the system itself was already pretty incredible and efficient. But of course, introducing the prefetcher and techniques will incur an even bigger speed up. What I did not like that well about the paper is that they did not explore the partitioning of the graphs all too well. They just did a random one where they put in the graphs into the cores and then just left it at that. They also tried some other methods, but that did not work too well. And as I will later see in the discussion, there are better ways to partition the graph. What is not so good is that even though they did concentrate on graph processing workloads, is that the entire system is perfectly suitable for other kinds of processors, like machine learning or genome analysis. They mentioned the pin count limitation as a huge problem for the external bandwidth. However, they did not go into too much detail on what exactly the pin count limitation itself is, or why it cannot be increased itself. Now, for example, the big problem is that physically it's just not too well impossible if the technology is limiting it, that you just can't increase the external bandwidth on a certain surface. And if there is, it's usually extremely expensive. They used in-order cores for the Tesseract system. They had the reasoning. However, since the entire evaluation was completely simulator-based, I would have still enjoyed to see that a usage of an out-of-order core for the Tesseract system, just to see if there was an actual speed-up boost from it, or if it would have brought any other benefits. And the programmable interface section, which I did not go over in this presentation, was a bit too short in my opinion. It was hardly a page, and it was some rather obvious stuff, and they just did not go into detail there. So coming to the discussion parts. So important part about Tesseract is it came out 2015. So of course, everything was a little bit different still there. So a big question is, what do you think, what kind of impact did the Tesseract system paper have on future systems that came out later? So here is a little timeline about it. So in 2011, we had the first hybrid memory cube really developed. 2013, hybrid memory cube 1.0 was published. And then in 2015, Tesseract itself came out, and the first big processor came out that used the hybrid memory cubes, but it did not specialize on it at all. It merely used it as a memory bandwidth amplifier. But then a couple years later in 2018, according to the retrospect on the Tesseract paper, came out the first processor that really was inspired by the Tesseract system. You could see that systems were being developed that really made emphasis on the technology of the hybrid memory cubes and other PIM measured based systems. So these, for example, are a couple of these papers. They were all announced in the retrospect paper, and they all, at least, were somewhat inspired by Tesseract in their opinion. So another big problem, since this came out in 2015, RowHammer wasn't that big of a problem yet. It wasn't really mentioned that much. So a big question would be, would Tesseract be vulnerable to RowHammer, or how badly would it be if that is the case? So the answer is yes, it would of course also be susceptible to RowHammer attacks. It is, after all, a dense memory structure that is based on the hybrid memory cube. This is, for one, mentioned in a retrospective on the RowHammer paper, and also in another paper that will be discussed in another seminar sometime in the future. So I won't talk much more about it here. As I already mentioned, the graph distribution system was, in my opinion, not too well explored. Do you think there is any, any of you think there is any improvement made to be? As mentioned, they just took the graph and randomly put it in the memory.
Yeah, I mean, I think it would help for processing in memory, right? If you were to place the graph in a way that you can exploit memory bandwidth.
Yep.
And the computation that you provide again adjacent to it.
Mm-hmm. So a big problem is that they had the message passing system, but of course, preferably you would not have to use it at all if all of the memory fetching would just be in the same vault. So Tesseract itself tried METIS, which is a partitioning graph partitioning process, which tries to reduce all of the edge links over every single vault connection. They did try this, however, they got little to no speed up at all. In some cases, it was even a negative speed up, and they completely ignored the overhead of employing METIS in this case. However, then there was another paper a few years later, and what they did is they tried to keep everything local by just ensuring that every outgoing edge would be at least with the same vertex of every vault. So at least they managed to cut down on the memory latency there somewhat. They actually achieved a 1.7 times speed up and about an 89% energy reduction on top of the already incredible results of Tesseract itself. Yeah, as already mentioned, they did not use out-of-order cores, but instead in-order cores. So do any of you have any thoughts on why they did not actually use out-of-order cores in the vault structure?
Does anyone have something to add? No, maybe not. Okay, then I think what would be the problem would be that maybe you don't have enough area to put in a full-blown out-of-order core, or because you put this on the bottom of the HMC, you may run into thermal issues, considering that an out-of-order processor might consume more power than an in-order processor because of all the register files that you need to maintain.
So memory out-of-order core usually helps with memory latency. It could still lead to some speed up. However, the entire system of Tesseract is designed such that there is hardly any memory latency, or it is decreased by a lot. And as Harsh already mentioned, there are power, area, and thermal limitations. And most of these would have been breached if an out-of-order core would have employed in that vault design. And the prefetching just makes it unnecessary mostly.
Yeah, but to add to that, maybe there could still be value in checking this again, right? There may be some scenarios, some use cases where this
which is
makes sense.
Yeah,
so I think it's a valid point that maybe there is value in checking whether an out-of-order core does really work for some nodes.
Yeah, like I said, I would have preferred it if they used an out-of-order core in the evaluation as well next to the normal Tesseract system they used.
Right.
So I presented the message triggered prefetcher that I showed you. So looking at this, the prefetcher fetches relevant data, but then it waits until several messages have arrived and all prefetch the data, and only then it will execute them. So can any of you think of any problem that might come from this system? If any of you looked at the vault structure exactly, you might have already seen the solution that Tesseract itself employs. So what they did, what the problem is that the data that gets prefetched before it actually is executed on is that it just might get evicted if it would go into normal cache, which is why that the message triggered prefetching has a special prefetch buffer in which it will use so that the cache won't be evicted before it actually is executed on. Yeah. And that's about it.
Well, does anyone else have any questions then? Go ahead.
Do we now have to rewrite all our graph algorithms?
No, the programming interface, wait. Yeah. They introduced these functions, and we saw the skeleton before for the PageRank computation. And this is basically what it would look like with the use of TestRec. They have their own application programming interface, and it would not make it too much more complicated. I think this could even be somewhat automated itself if you, like, without too much work.
Okay, then any other questions?
So I was actually intrigued that you mentioned RowHammer, and I was wondering if you had any specific thoughts of how it would be worse in this scenario.
So the DRAM technology would of course be the same as other memory, normal main memory, like in a DDR3 based system. But in this case, since it is 3D, there might be some case that the lower layers could also affect the upper layers, and with all of the heat and the electricity that goes through there, I think it could be even way worse than a normal 2D based system.
Okay, thank you. That makes sense.
I think maybe if I can add to your point, there is yet another work from Safari that characterizes RowHammer and HBMs. They see that the impact of temperature with RowHammer exists. So maybe when you compute in the lower dies with auto cores and in auto cores, maybe you increase temperature, and then that can cause an increased possibility of running into RowHammer. So yeah. Plus, added to the fact that you've already mentioned that there is another work which is going to be discussed in another seminar on processing using memory, though, not processing near memory.
Oh, right.
We still need to check if processing near memory can inherently cause RowHammer. But that's it then. Unless anyone else has other questions. Oh, one more. Okay. Oh, good.
So for a normal memory, you have some kind of vendor-specific defenses against RowHammer, like target row refresh. Is there anything similar in this HBM?
I have searched for that. I have hardly found anything except for this paper that Harsh just mentioned, but I haven't looked too much into that. Also, it's generally just not that much looked into.
Okay.
Yeah, I mean, if I may add, for HMC, this probably doesn't exist because it's sort of a dead technology. With HBM, you still have something like that. Yeah. Well, I hope. I'm not sure. Could probably check this. Okay, done. I guess we're at the end of this.
Then I guess let's thank one last time our speaker. So this concludes today's session. So everyone, please, a reminder to fill in the quiz and the feedback to the presenters and your mentors. There was an issue with the feedback to the presenters, which I have fixed now. So you can find there a long text where you can enter your feedback. Okay. Thank you.